Hello everyone, I am Sultan Alhusain and today I am going to present my paper entitled Predicting Relative Thresholds for Object-Oriented Matrix. There exist many proposed and empirically validated object-oriented matrix, the main aim of which is to facilitate the production of quality software products by providing a numerical characterization of quality attributes. However, with any metric we use, we need to know what is too low or too high. In other words, we need to be able to objectively interpret its values, and thresholds are basically the reference points that makes it possible to do so. Matrix, along with the reference points, can be used in constructing quality attributes and informing design decisions. They can also be used to optimally allocate testing resources and to identify classes with undesirable quality attributes. In the context of technical debt, metric thresholds have been used to classify debt levels into green, yellow, and red status levels in a threshold-based approach to calculate technical debt. They have also been used to develop a technical debt assessment framework, which uses detection rules that are built based on metric thresholds. These are just two examples for how thresholds are used to assess technical debt. And of course, having better thresholds helps to improve or helps to get more accurate assessment of technical debt. The question now is, how are thresholds determined? This is done using one of the following main approaches. The first of which is based on the experience of individuals, but such thresholds have no or little data support. The means with standard deviations have also been used to calculate thresholds. One problem with this approach is the assumption that metric values are normally distributed, whereas in fact most of them are not. Also, using probability distribution functions on a data set of an individual system or aggregated data sets from multiple systems to calculate the value that represent 80% of the classes, for example, and then use this value as a threshold to identify the remaining 20% of the potentially problematic classes. The last approach is using logistic regression model, or more precisely, a manipulated version of it. This manipulated version calculates a value or a threshold based on a given probability level, instead of the other way around, as is the case in the original model. We will discuss this model later. But I would like to note for now that, unlike the previous approaches, the data required by this approach must also include information about an external quality of interest, the presence or absence of defects in software classes, for example. While this is an advantage for this model compared to the previously discussed one, it still has some problems. We will discuss these problems in later slides and propose solutions for them. Overall, the main shortcomings of previous approaches are, most of them are distribution based and uses no quality data, which leads to unreliable thresholds as found by a previous study. Also, contextual variables are not considered in most threshold studies. Context is a critical factor to consider. A reasonable and useful threshold in one context may not be so in another. Thus, there are still no universally accepted thresholds, even for the most studied matrix, and the effective application of matrix has generally been limited. In this paper, we will focus on software size as a contextual factor for several reasons. First, most object-oriented matrices follow a power law distribution. So the largest value of this matrix increases with the number of classes in a software system. The relationship between software size and the range of values this relationship between software size and the range of values of coupling matrix in particular was observed by C and K in their seminal 1994 paper, in which they note that coupling between classes is an increasing function of the number of classes in the application. So an exceedingly high coupling metric value in one system may be relatively low in a small system, may be relatively low in a large one. The selection of this contextual factor is also motivated by the fact that system size can easily be incorporated into mathematical models that are used to estimate thresholds. The relationship between software size and the range of metric values has apparently affected the thresholds calculated using different calculation methods. The table shows the thresholds calculated for 5 metrics using 3 different approaches as reported by their authors, and you can notice the trend of positive relationships. Similar observations of a positive trend have also been reported by others. In this paper, the relationship between system size as a contextual factor and metric thresholds is investigated. The objective are to build predictive models that estimate thresholds based solely on system size and to assess the feasibility of this approach as a threshold estimation method. In the following slides, I will describe and discuss the methodology followed to achieve the objectives, which consist of these 5 steps. A total of 36 defect datasets are used in this study. The datasets are obtained from 2 publicly available repositories. Since we are using datasets from different repositories which are likely to be inconsistent, they were all regenerated using a single tool. Each dataset contains a list of classes for which metric values are calculated, along with information about the presence or absence of defect in each class. These metrics are the ones included in the study, and they were selected to cover different quality aspects from different perspectives and focus. Their definitions and full citations are provided in the article for those interested. To examine the size threshold relationship and subsequently build the threshold estimation models, we first need to calculate thresholds for the 6 metrics in the 36 systems. The model used to calculate these thresholds is a logistic regression-based threshold model. The input to the original LR model, as you can see, is the value of a metric X in a class, and the output is the probability or risk that the class has a defect. Alpha and beta are the coefficients to be estimated when fitting the datasets. With some algebraic manipulations, this original model can be transformed into the LR threshold model. The input to the LR threshold model is the acceptable risk level, or we can say here the acceptable defect probability. The output is the metric value at the given acceptable risk level, which is used as a threshold. This LR threshold model was originally introduced in the field of epidemiology, but later adopted and used in several software engineering studies. However, there are 2 problems with this LR threshold model. The first problem is the generation of negative thresholds for some risk levels, as reported by multiple authors in the literature. After examining this issue, the cause for the negative thresholds was found to be the setting of acceptable risk levels that are below background risk levels. The background risk level is the risk when the metric value equals 0. So when the randomly selected acceptable risk levels happens to be below the background risk, the thresholds calculated goes below 0. The solution I propose is to calculate the acceptable risk level as an increase to the background risk level. The second problem is caused by using imbalanced datasets. This imbalance affects one of the coefficients of the LR model, and it leads to an underestimation or overestimation of the risk, which consequently affect the calculated threshold values. The solution is to simply use a correction technique already proposed in the literature. These 2 solutions are described in detail in the article. After fitting the LR model for the CPU metric, for example, on the datasets of the 36 systems, and then using the LR threshold model to calculate the thresholds, we get a list of 36 size threshold pairs, a snippet of which is shown in this table. These pairs of sizes and thresholds are going to be used in the following correlation analysis. The size threshold correlation analysis is done using the Spearman rank correlation coefficient. The correlation coefficients shown in this table are calculated before and after applying the imbalance correction at 3 different levels of acceptable increase to the background risk. We can see that all metric thresholds except those for WMC have a significant positive correlation with software size, but only after the correction is applied. This demonstrates the impact of data imbalance and supports the imbalance, or supports the importance of considering its effect on in similar studies. In order to develop the threshold estimation models, linear regression models are used to fit the size threshold pairs of each metric. These models can then be used to estimate thresholds. These estimation models relate the independent variable of system size to the dependent variable of threshold. The models are then used to estimate a threshold for each system. I should note here that the model used to estimate a metric threshold in a system is not fitted on any data coming from that system, nor any data from its other versions. This is done to be sure that the estimation models are appropriately tested and its performance in other unseen systems evaluated properly. The threshold evaluation models are evaluated based on the accuracy with which their thresholds can classify classes into faulty and non-faulty category. The same evaluation is also done for the LR, that is logistic regression threshold models, in order to assess the effect of applying the imbalance correction on the classification accuracy. The impact of applying the correction on the classification accuracy of the LR model threshold is showing in this figure. It can be clearly seen that the correction has a positive impact on the accuracy of all metric thresholds, as demonstrated by the increase in the median G-mean for all metrics. The accuracy improvement is particularly clear in CBO, DCC, and NOM metrics. This figure shows a comparison between the classification accuracy of the LR model thresholds after correction, of course, and the estimation model thresholds. These thresholds of both models, or the thresholds of both models, have a similar overall accuracy for all metrics apart from the import and export coupling metrics. The estimation model has better accuracy in the former metric and worse in the latter one. It is nevertheless interesting that the estimation models has achieved an accuracy comparable to that of the LR threshold model, considering that the LR model has a full exposure to the metric values and defect probabilities in the test systems themselves, whereas the estimation model is built on only the size threshold pairs from other systems. These shows the classification accuracy of different metric. I think I would need to skip this slide for time. The results show that the proposed threshold estimation method is feasible. They can also be used to calculate relative thresholds even in systems that lack historical quality related data. The improved LR threshold model produced better thresholds, as we have seen. And thank you very much.
Enjoy the next. Yes, so welcome to the second session related to smile patterns and metrics. I am Valentina Lenarduzzi from Alhusain University, and we have two papers in this second session. The first paper is presented by Sultan Alhusain, and the title is Predicting Relative Threshold for Object-Oriented Metrics. We have 15 minutes of presentation as usual for the other section, and then a couple of minutes for question. So please, the stage is yours, Sultan.
Hello everyone, I am Sultan Alhusain, and today I am going to present my paper entitled Predicting Relative Thresholds for Object-Oriented Metrics. There exist many proposed and empirically validated object-oriented metrics, the main aim of which is to facilitate the production of quality software products by providing a numerical characterization of quality attributes. However, with any metric we use, we need to know what is too low or too high. In other words, we need to be able to objectively interpret its values, and thresholds are basically the reference points that makes it possible to do so. Metrics, along with their reference points, can be used in constructing quality attributes and informing design decisions. They can also be used to optimally allocate testing resources and to identify classes with undesirable quality attributes. In the context of technical debt, metric thresholds have been used to classify debt levels into green, yellow, and red status levels in a threshold-based approach to calculate technical debt. They have also been used to develop a technical debt assessment framework, which uses detection rules that are built based on metric thresholds. These are just two examples for how thresholds are used to assess technical debt. And of course, having better thresholds helps to improve or helps to get more accurate assessment of technical debt. The question now is, how are thresholds determined? This is done using one of the following main approaches. The first of which is based on the experience of individuals, but such thresholds have no or little data support. The means with standard deviations have also been used to calculate thresholds. One problem with this approach is the assumption that metric values are normally distributed, whereas in fact most of them are not. Also using probability distribution functions on a data set of an individual system or aggregated data sets from multiple systems to calculate the value that represent 80% of the classes, for example, and then use this value as a threshold to identify the remaining 20% of the potentially problematic classes. The last approach is using logistic regression model, or more precisely, a manipulated version of it. This manipulated version calculates a value or a threshold based on a given probability level, instead of the other way around, as is the case in the original model. We will discuss this model later. But I would like to note for now that, unlike the previous approaches, the data required by this approach must also include information about an external quality of interest, the presence or absence of defects in software classes, for example. While this is an advantage for this model compared to the previously discussed one, it still has some problems. We will discuss these problems in later slides and propose solutions for them. Overall, the main shortcomings of previous approaches are, most of them are distribution based and uses no quality data, which leads to unreliable thresholds as found by a previous study. Also, contextual variables are not considered in most threshold studies. Context is a critical factor to consider. A reasonable and useful threshold in one context may not be so in another. Thus, there are still there are still no universally accepted thresholds even for the most studied matrix, and the effective application of matrix has generally been limited. In this paper, we will focus on software size as a contextual factor for several reasons. First, most object-oriented metrics follow a power law distribution. So the largest value of this matrix increases with the number of classes in a software system. The relationship between software size and the range of values this relationship between software size and the range of values of coupling matrix in particular was observed by C and K in their seminal 1994 paper, in which they note that coupling between classes is an increasing function of the number of classes in the application. So an exceedingly high coupling metric value in one system may be relatively low in a small system, may be relatively low in a large one. The selection of this contextual factor is also motivated by the fact that system size can easily be incorporated into mathematical models that are used to estimate thresholds. The relationship between software size and the range of metric values has apparently affected the thresholds calculated using different calculation methods. The table shows the thresholds calculated for 5 metrics using 3 different approaches as reported by their authors, and you can notice the trend of positive relationships. Similar observations of a positive trend have also been reported by others. In this paper, the relationship between system size as a contextual factor and metric thresholds is investigated. The objectives are to build predictive models that estimate thresholds based solely on system size and to assess the feasibility of this approach as a threshold estimation method. In the following slides, I will describe and discuss the methodology followed to achieve the objectives, which consist of these 5 steps. A total of 36 defect datasets are used in this study. The datasets are obtained from 2 publicly available repositories. Since we are using datasets from different repositories which are likely to be inconsistent, they were all regenerated using a single tool. Each dataset contains a list of classes for which metric values are calculated, along with information about the presence or absence of defect in each class. These metrics are the ones included in the study, and they were selected to cover different quality aspects from different perspectives and focus. Their definitions and full citations are provided in the article for those interested. To examine the size threshold relationship and subsequently build the threshold estimation models, we first need to calculate thresholds for the 6 metrics in the 36 systems. The model used to calculate these thresholds is a logistic regression-based threshold model. The input to the original LR model, as you can see, is the value of a metric X in a class, and the output is the probability or risk that the class has a defect. Alpha and beta are the coefficients to be estimated when fitting the datasets. With some algebraic manipulations, this original model can be transformed into the LR threshold model. The input to the LR threshold model is the acceptable risk level, or we can say here the acceptable defect probability. The output is the metric value at the given acceptable risk level, which is used as a threshold. This LR threshold model was originally introduced in the field of epidemiology, but later adopted and used in several software engineering studies. However, there are 2 problems with this LR threshold model. The first problem is the generation of negative thresholds for some risk levels, as reported by multiple authors in the literature. After examining this issue, the cause for the negative thresholds was found to be the setting of acceptable risk levels that are below background risk levels. The background risk level is the risk when the metric value equals 0. So when the randomly selected acceptable risk levels happens to be below the background risk, the thresholds calculated goes below 0. The solution I propose is to calculate the acceptable risk level as an increase to the background risk level. The second problem is caused by using imbalance datasets. This imbalance affects one of the coefficients of the LR model, and it leads to an underestimation or overestimation of the risk, which consequently affect the calculated threshold values. The solution is to simply use a correction technique already proposed in the literature. These two solutions are described in detail in the article. After fitting the LR model for the CPU metric, for example, on the datasets of the 36 systems, and then using the LR threshold model to calculate the thresholds, we get a list of 36 size threshold pairs, a snippet of which is shown in this table. These pairs of sizes and thresholds are going to be used in the following correlation analysis. The size threshold correlation analysis is done using the Spearman rank correlation coefficient. The correlation coefficients shown in this table are calculated before and after applying the imbalance correction at 3 different levels of acceptable increase to the background risk. We can see that all metric thresholds except those for WMC have a significant positive correlation with software size, but only after the correction is applied. This demonstrates the impact of data imbalance and supports the imbalance, or supports the importance of considering its effect on in similar studies. In order to develop the threshold estimation models, linear regression models are used to fit the size threshold pairs of each metric. These models can then be used to estimate thresholds. These estimation models relate the independent variable of system size to the dependent variable of threshold. The models are then used to estimate a threshold for each system. I should note here that the model used to estimate a metric threshold in a system is not fitted on any data coming from that system, nor any data from its other versions. This is done to be sure that the estimation models are appropriately tested and its performance in other unseen systems evaluated properly. The threshold evaluation models are evaluated based on the accuracy with which their thresholds can classify classes into faulty and non-faulty category. The same evaluation is also done for the LR, that is logistic regression threshold models, in order to assess the effect of applying the imbalance correction on the classification accuracy. The impact of applying the correction on the classification accuracy of the LR model threshold is showing in this figure. It can be clearly seen that the correction has a positive impact on the accuracy of all metric thresholds, as demonstrated by the increase in the median G-mean for all metrics. The accuracy improvement is particularly clear in CBO, DCC, and NOM metrics. This figure shows a comparison between the classification accuracy of the LR model thresholds after correction, of course, and the estimation model thresholds. These thresholds of both models, or the thresholds of both models, have a similar overall accuracy for all metrics apart from the import and export coupling metrics. The estimation model has better accuracy in the former metric and worse in the latter one. It is nevertheless interesting that the estimation models has achieved an accuracy comparable to that of the LR threshold model, considering that the LR model has a full exposure to the metric values and defect probabilities in the test systems itself or themselves. Whereas the estimation model is built on only the size threshold pairs from other systems. These shows the classification accuracy of different metric. I think I would need to skip this slide for time. The results show that the proposed threshold estimation method is feasible. They can also be used to calculate relative thresholds even in systems that lack historical quality related data. The improved LR threshold model produced better thresholds as we have seen. And thank you very much.
So thank you very much, Sultan, for your presentation. There are questions from the audience that you want to write in the chat, and I will provide immediately to Sultan. So there are questions? No, so I can provide question to you. The first question is, I'm wondering about the selection of the software metrics that you consider. So how can you explain better the selection of the metrics? So why this list and not included other one, for example?
Okay. The metrics, can you hear me?
Yeah, I can hear you.
Okay. The metrics selected are basically the covers the coupling matrix and complexity matrix.
Yeah.
The cohesion matrix, for example, were not considered because most of them the well-known cohesion matrix are bounded. Their values are bounded between 0 and 1. Mm-hmm. So they value do not. I mean, they are not open-ended, if I say it correctly. That's one reason for excluding the other reason for excluding cohesion matrix is that the other cohesion matrix that are not bounded with values that are not bounded have problems in their values, well-documented problems that are reported in the literature. So, like for example, the ILCOM matrix, if you know it, it has been reported that it gives same value for classes with different cohesion levels. That's for the cohesion matrix. With regard to the other matrix that I have selected for the coupling and complexity, I have explained in the paper that I have chosen the matrix that covers each one of these two aspects from different perspectives. For example, the CBO metric covers the outgoing and incoming coupling at a certain level, whereas the DCC metric covers only the coupling at the attribute and method parameter level.
Okay.
With regard to the complexity, for example, with regard to the complexity matrix, I have used the most well-known one, which is WMC. And when you consider the weight of each method to be unity, that will simply be the number of, it will be, the metric will be simply the count or the number of methods, which is the number of method NOM metric. That's, I hope I explained that. That's the